Section 12.4 talks about compositional functions. So first let's look at the formal definition. So suppose we have a function f from a to b and g from b to c. And those are functions with the property that the codomain of f, so that b, is equal to the domain of b, that g. Then we can define the composition of f with g to be another function, denoted g compose f, and it's defined by, given some x in a, so we're starting with something in f, we first do f to that x, and then we do g. So g compose f of x is g of f of x. So it sends elements from a all the way to c. So let's look at some examples here. So starting off, right, maybe I have the function f here. It's going to map a to b. It doesn't have to necessarily be one-to-one or onto. And now my b is going to map, my g is going to map b to c. So it has to have somewhere for everybody in b to go. So notice here, right, the codomain, the b set for my function f, it wasn't an onto function. So I didn't map everything there, but I did need all of those elements in b to be in the domain of g. So I did have to have arrows for each of those. And now we can think about the composition, right? So for this 1, first f sends 1 to a, and then g sends a to star. So g compose f is going to send 1 to star. F sends 2 to a, g sends a to star, so 2 also gets sent to star. And then f sends 3 to c, g sends c to star, so 3 gets sent to this other star here. So that's what my f compose g is going to be. So you should be familiar with this sort of idea, but now we're just sort of seeing it in this new diagrammatic approach. Okay, so let's look at one more example here. I've got 3 functions, f, g, and h, and I've given tables for each of those. And I want to know which ones I can compose. So in order to compose functions, I need the codomain of one to equal the domain of the next. And really I just need the range, the outputs, to be a subset of the domain of the next function. So here, for each of my functions, let's write down what the domain is. So here my domain for f is a, b, c, and that's mapping to the set 0, 1. Right, so this is one option for my codomain, but I could have also said something like 0, 1, 2, right, because I don't necessarily need to hit everything in my codomain. But I'm just going to call that 0, 1 for now. We'll do the same thing for g. G is going from that set 0, 1 to 1, 3. And then h is going from 1, 2, 3 to 0, 1. So which ones can I compose? So f starts at a, b, c, goes to 0, 1. G starts at 0, 1, goes to 1, 3. So I can do f compose g. And that will start at a, b, c, go through 0, 1, and end up at 1, 3. Now, 0, 1 is not a subset of 1, 2, 3, so I can't compose those. But 1, 3 is a subset of 1, 2, 3. So if I do g first, I can do h next. And that'll go from 0, 1 to 0, 1. So let's go ahead and write out the tables for each of these. So for my function g compose f, I start with a. A gets mapped to 0 by f, and then 0 gets mapped to 3 by g. So that's going to be 3. B, c. B gets mapped to 1 by f. 1 gets mapped to 1 by g. So that's 1. And then c goes to 0. 0 goes to 3. So that's 3 as well. And then for my h compose g, my inputs are 0 and 1. 0 gets mapped to 3. 3 gets mapped to 1. So 0 goes to 1 by the composition. 1 gets mapped to 1, and then that 1 gets mapped to 0 by h. So my function from G compose H, or sorry, H compose G, so doing H first, G first, oh man, let me actually write it out. So this one is H compose G, but we have to think about doing G first. And the way that we think about that, right, is that we're going to actually put the X here. So the closest thing to the X is G, and then we do that H next. All right, so question, is the composition commutative? Let's look at this specific example and see what we get. So I want to look at F compose G of X and G compose F of X. So F compose G, by definition, that's just F of G of X. G of X is just X plus 2. So I'm just going to plug in X plus 2 for the X in F. So that's going to be X plus 2 quantity squared plus 1, which is X squared plus 4X plus 4, plus that 1 is 5. Now if I do G compose F, that's G of F of X. So that's G of F of X is X squared plus 1. So that's going to be X squared plus 1 plus 2, or X squared plus 3. And we notice that these are not equal. So we can see, using this counterexample, that composition is not commutative. So we have to be careful with the order when we're doing these compositions. All right, next question, is composition associative? So we have to remember what associative means here. So that's the same as asking if I have a composition of 3 different things. All right, so let's say that F is a function from A to B. That's fine. And let's start with H just so that we can work our way inside out. H is a function from A to B. G is a function from B to C. And then finally, F is a function from C to D. So I have these 3 things here. If I have 3 things like that, there's 2 ways I can think about ordering them. I can think about doing F compose with the function G compose H, or I can think about doing F compose G composed with H. And when I'm asking if it's associative, I'm asking if those 2 are equal to each other. So let's say I have some X that can go into H. So let's let X be an A. Then what does F compose G compose H of X look like? Well, by definition, that's just going to be first plug X into G compose H, which is just G of H of X. And then we're going to plug that into F. Make sure we get all the parentheses there. But if instead I do F compose G compose H of X, well, I'm still going to take the X, I first plug it into H, I plug that into G, or F compose G, so I'm going to still plug that in here. So we notice that those are the same as each other. So we do get that composition is associative. There's really only one thing I can do, independent of which order I write it. Okay, so let's wrap up with a discussion question here. Suppose you have 2 functions, f from a to b and g from b to c. I want you to think about the following 2 things. So if f and g are injective, you want to show that their composition is injective. And if they're surjective, both surjective, show that their composition is surjective. So we'll talk about this in class on Thursday.